Okay, so we're back, and we've talked a little bit about some units with electricity and other things in physics, but now we're going to talk some more about current. And I'm going to use the analogy to water flow. If you can imagine water flowing in pipes, that's sort of the analogy that we're going to use here. And voltage can basically be looked at as, by analogy, can be viewed as the pressure that drives the flow of charge, rather than in water pipes, it's the water pressure that drives the flow of water. So it drives the flow of charge. Right. So another way of looking at voltage is we can talk about voltage as being the difference in electrical potential between 2 points. So in other words, the difference in pressure between 2 points. And another key thing to know about voltage, and you can see here as I'm talking about electrical currents and water flow, a big idea here is for us to start talking about voltage, right? That's one of the big ideas. Voltage is always measured from place to place, essentially. So it's like altitude. If you think about altitude, when we say that when we're on a mountaintop and we're 2,000 feet high, 2,000 feet compared to what? Well, we always measure altitude, or often, from sea level. Voltage is always measured from place to place. So if we're looking at a circuit, it'll be a voltage drop from one part of the circuit to another or something like that. It's essentially a relative measurement from one place to another. And lastly, we can look at it as energy, which we defined energy in the last video, divided by charge. So, which, since energy was force times distance, it's force times distance divided by charge. So, if electricity is water flow through a pipe, then voltage is the pressure, and basically that's what pushes the water. And current is the flow of water. And I pick water because we can see water. It's tough to see electrons. Water is the charge. That's what's flowing in electricity. The electrons. And the resistance is how big or small the pipe is, for example. Alright, that's just one way to look at this. And while we're here, we can define current. The idea of current is simply the flow of charge per time. So the flow of charge over time. So we have our unit for charge, which is the coulomb. So coulomb per second. That's current. And another name for that is the ampere. That's So, and we usually abbreviate that to amps. So when we're talking current, we talk about amps, which is coulombs per second. So next I want to talk about electrical power. And we defined power before. So since current is equal to charge per second, right? And voltage is equal to energy per charge. We've defined those. Then we can look at power as being equal to voltage times current. And let's see why. Because voltage, right? There we go. Voltage, energy per charge. And current, charge per second. Well, we can, when we multiply those together, we can cross the charges out top and bottom, and we're left with energy per second, which energy over time, we already decided that this was power. And just so everybody's clear, a lot of times we'll write this equation, right? We'll write that as P equals V times I, or just P equals VI. And for some reason, I is the abbreviation for current. It's lost to me, but there it is. I is the abbreviation for current. So again, power is the voltage times the current. That gives us power. So to finish this water analogy, when we talk about alternating current, we want to talk about how the current actually flows in two directions in an electrical circuit. So what I've got here is a picture. I downloaded it from that SparkFun website. This is a rotating type motor, which is going to draw this piston back and forth, back and forth. And when the piston goes this way, right, it's going to push water around the circuit in that direction. So when that goes that way, the water is going to get pushed around. However, this thing's going to keep rotating, and then that piston's going to go back the other direction. So it's going to go that way. And when that happens, it's going to push the water around this way in the circuit. And the water's just going to kind of keep going back and forth through the circuit. That's essentially like alternating current. In terms of direct current, it just goes one direction, so just one way. So if I was to graph what direct current looks like, and we were to graph voltage, right, versus time, what we would find for direct current is that the voltage is a constant. One direction just goes out, assuming that we don't have a variable voltage type circuit, but one direction, boom, there you go. That's direct current. However, that's direct current. If we were to look at alternating current, that's not what we would find. So for alternating current, same graph, right? Voltage and time. What we would find there is that we would continually go back and forth between positive and negative voltage. And typically that's modeled as a sine wave. And in this case, the pressure in the pipe changes direction, right? So the pressure changes direction. For alternating current, whereas for direct current, the pressure is constant in one direction, right? So here the pressure is constant in one direction. And in the U.S., essentially the voltage in our circuits, in the circuits you're familiar with in your house, the voltage is 120 volts. That's the voltage that your house will be running on. And this thing flips direction 60 times per second. So flips 60 times per second. Or you might hear that it's running at 60 hertz, right? 60 hertz, which hertz is just cycles per second, so 60 times per second in the U.S. It's not that way everywhere in the world, but in the U.S., typically our residential electricity is running at 120 volts, 60 hertz, flipping back and forth. And that has some impacts to a lot of the things we do. But we're not going to get that much into that.